On the evening of April 13th, 2029, something will happen that has never happened before in recorded human history. A rock the size of a skyscraper, 370 meters across, weighing roughly 27 billion kilograms, will slide between the Earth and the ring of satellites that carry our television signals, our GPS coordinates, and our weather data. It will pass closer to us than the Moon, closer than the International Space Station's orbit, closer, in fact, than some of the communication satellites you rely on every single day without thinking about them. Its name is Apophis, and for a brief window of time, it will be visible to the naked eye. Not through a telescope, not through binoculars. If you stand outside on that April evening and look up at the right patch of sky, you will see a point of light drifting among the stars. That point of light is not a star. It is not a plane. It is a mountain of iron and nickel hurtling through the vacuum of space at roughly 31 kilometers per second, close to 112,000 kilometers per hour. And it will be so close that you could, in theory, point a sufficiently powerful laser at it and watch the beam bounce back in a fraction of a second. Let that number settle for a moment. 31,860 kilometers. That is how close Apophis will come to the surface of the Earth. To put that in perspective, the Earth itself is about 12,742 kilometers in diameter. Apophis will pass at a distance of roughly 2.5 Earth widths from the ground beneath your feet. Geostationary satellites, the ones that beam down your cable television and relay your long-distance phone calls, orbit at about 35,786 kilometers above the equator. Apophis will dip below that line. It will, for a few breathless hours, be closer to you than the infrastructure of modern communication. And here is where the story takes its darker turn. When Apophis was first discovered in June of 2004, astronomers did not know it would miss. For several terrifying months, the initial calculations suggested something far worse, a direct impact with Earth in 2029. The probability climbed as high as 2.7%. That might sound small. It is not. In the world of asteroid hazard assessment, a 2.7% chance of impact is a screaming alarm. It was the highest probability of collision ever recorded for any known asteroid. For a brief period, Apophis was assigned a rating of 4 on the Torino Impact Hazard Scale, a level that had never been reached before and has never been reached since. The language at that level reads, "A close encounter, meriting attention by astronomers. Calculations give a 1% or greater chance of collision capable of regional devastation." Regional devastation. That phrase was not chosen lightly. If Apophis were to strike the Earth, the energy released would be roughly 1,100 megatons of TNT. That is more than 20,000 times the energy of the atomic bomb dropped on Hiroshima. An impact in the ocean would generate tsunamis capable of erasing coastlines. An impact on land would create a crater several kilometers across and throw enough debris into the atmosphere to alter weather patterns across the globe. Entire nations could be affected. Millions of lives could end in minutes. And this object is coming back. On April 13th, 2029, Apophis will not hit us. The updated orbital calculations have confirmed that, and we will walk through exactly how scientists reached that conclusion tonight. But the flyby itself will be the closest approach of an asteroid this size that humanity has ever witnessed. And it raises a question that no amount of reassurance can fully silence. What happens the next time? What happens when the next Apophis is found, and the math does not work out in our favor? By the end of tonight, you are going to understand exactly what Apophis is, where it came from, why it terrified the world's best astronomers, and what its close pass in 2029 will actually look like from the ground. You are going to understand how we track objects like this, why our defense systems are still alarmingly incomplete, and what this single rock reveals about the fragile thread on which civilization hangs. This is not a story about panic. It is a story about awareness. The moment humanity looked up and realized, with scientific certainty, that the sky is not as safe as it seems. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now let us begin. To understand why Apophis matters, you first need to understand what it is. And to understand what it is, you need to understand the neighborhood it comes from. Our solar system is not the orderly, clean diagram you remember from school textbooks. Those neat illustrations, sun in the center, 8 planets spaced evenly on circular orbits, everything quiet and well-behaved, are lies of simplification. The real solar system is a shooting gallery. Between and beyond the planets, there are millions upon millions of leftover fragments from the era of planetary formation. Rocky debris, metallic shards, icy remnants, some are the size of grains of sand, some are the size of small moons, and they are not sitting still. They are orbiting the sun on paths that weave and cross and, occasionally, intersect the orbit of Earth. These are the asteroids, and the specific class of asteroid that Apophis belongs to is called an Aten-type near-Earth asteroid. That classification is important, so let us break it down. A near-Earth asteroid is any asteroid whose orbit brings it within roughly 1.3 astronomical units of the Sun, close enough that its path can cross or approach the orbit of Earth. An Aten asteroid is a subcategory. Its orbit has a semi-major axis smaller than Earth's, meaning it spends most of its time inside Earth's orbit closer to the Sun. But its orbit is elliptical, stretched, and on the outward swing of that ellipse, it crosses Earth's path. Think of it like 2 cars on a highway. Earth is driving in its lane at a steady speed, completing 1 loop around the Sun every 365.25 days. Apophis is on a different highway, one that is slightly tilted, slightly eccentric, and slightly faster on some stretches. Most of the time, the 2 cars are nowhere near each other, but twice during every orbit of Apophis, their highways cross, and if both cars happen to reach the intersection at the same time, the consequences are unthinkable. Apophis completes 1 orbit around the Sun every 323.6 days. That is about 42 days shorter than Earth's year. Its orbit is tilted about 3.3 degrees relative to Earth's orbital plane, and it has an eccentricity of about 0.191, meaning it is noticeably more elliptical than Earth's nearly circular path. At its closest to the Sun, it's perihelion. Apophis dips inside the orbit of Venus, reaching about 0.75 astronomical units from the Sun. At its farthest, it's aphelion. It swings out to about 1.1 astronomical units, just beyond Earth's orbit. It is a cosmic commuter, weaving between the inner planets on a path shaped by the gravitational influence of every massive body it passes. Now, the discovery. The story of how we found Apophis is, in itself, a lesson in how close we came to missing a potential catastrophe. On the night of June 19, 2004, at the Kitt Peak National Observatory in Arizona, 2 astronomers named Roy Tucker, David Tholen, and Fabrizio Bernardi spotted a faint point of light moving against the background stars. This was not unusual. Asteroid surveys detect moving objects regularly. The object was catalogued with a provisional designation, 2024 MN4. The astronomers tracked it for 2 nights, recorded its positions, and then, as sometimes happens, the object was lost. It moved into a region of sky too close to the Sun to observe, and the data was filed away. For 6 months, nobody thought about it. Then, in December of 2004, astronomers at the Siding Spring Observatory in Australia rediscovered the object. It was given a new provisional designation before anyone realized it was the same object spotted at Kitt Peak 6 months earlier. When the 2 sets of observations were combined, the June data and the December data, the orbital calculation became far more precise, and the result was alarming. The newly refined orbit showed that this asteroid would make an extremely close approach to Earth on April 13, 2029. The initial uncertainty in its trajectory was large enough that an impact could not be ruled out. In fact, the probability of impact climbed rapidly as more observations poured in. Within days, the object was formally named 99,942 Apophis after the ancient Egyptian deity of chaos and destruction, the serpent god, who was said to dwell in eternal darkness and threaten to swallow the sun. The name was not chosen at random. The astronomers who named it understood the mythological weight. In Egyptian cosmology, Apophis, also known as Apep, was the embodiment of everything that opposed order, light, and life. Every night, as the sun god Ra sailed through the underworld, Apophis would attack, trying to consume the solar boat and plunge the world into permanent darkness. The gods would fight back, and Ra would emerge at dawn. But the threat never ended. Apophis could never be permanently destroyed. He would always return. It was, in retrospect, a chillingly appropriate name for an asteroid that refuses to go away. Let us talk about scale, because the numbers alone do not convey what Apophis actually is. 370 meters across. That is its estimated diameter. If you stood at one end of Apophis and looked toward the other end, you would be looking at a distance roughly equivalent to the height of the Empire State Building. The full structure, from ground to antenna tip. Picture that building lying on its side, tumbling slowly through space at a speed that would cross the entire United States in about 5 minutes. But Apophis is not shaped like a building. Radar observations from the Goldstone Deep Space Communications Complex in California, conducted during Apophis's close approach in March of 2021, revealed that the asteroid has an elongated, bilobed shape, something like a peanut or two large boulders fused together. Its surface is likely covered in loose rubble called regolith, mixed with larger rocks and possibly deep fractures. It rotates roughly once every 30.4 hours, and it also wobbles, a non-principal axis rotation that makes it tumble slightly as it spins, like a poorly thrown football. Its composition is classified as type SQ, a silicate-rich body with some metallic content. This means it is primarily rock and metal, not ice or loose dust. If you could hold a piece of Apophis in your hand, it would feel like a dense, dark stone, similar to certain types of meteorites found on Earth. The density of the asteroid is estimated at roughly 2.6 grams per cubic centimeter, which puts it in the range of solid rock with some internal porosity. It is not a solid iron cannonball, but it is not a loose pile of gravel either. It sits somewhere in between, and that distinction matters enormously when calculating what would happen in a collision. Now, to truly grasp how close 31,860 kilometers is in cosmic terms, consider this. The Moon orbits at an average distance of about 384,400 kilometers. Apophis will pass at roughly 1/12 of that distance. If you shrank the Earth-Moon system down so that the Earth was a basketball sitting on your kitchen table, the Moon would be a tennis ball about 7.4 meters away. Across the room, maybe in the hallway, in that same model, Apophis would pass at roughly 62 centimeters from the basketball, less than an arm's length, close enough to reach out and touch. And here is a detail that rarely makes the headlines. At that distance, Apophis will be close enough for Earth's gravity to measurably alter its orbit. The encounter in 2029 is not just a flyby, it is an interaction. Earth's gravitational field will bend Apophis's trajectory, changing its orbital period, its inclination, and its relationship with every other body in the inner solar system. The asteroid that enters Earth's neighborhood on April 13th will leave on a different path than the one it arrived on. In orbital mechanics, this is called a gravitational keyhole, a precise region of space where, if the asteroid passes through it, the gravitational deflection will set it on a future collision course. In the early years after Apophis's discovery, one of these keyholes was the source of enormous concern. If Apophis passed through a keyhole roughly 600 meters wide during the 2029 flyby, it would return in 2036 on a direct impact trajectory. 600 meters. In the vastness of space, that is less than nothing. A window smaller than a city block, hidden in the darkness between planets. And for several years, scientists could not confirm whether Apophis would thread that needle. To understand why the uncertainty persisted for so long, you need to understand something about how asteroid orbits are calculated. When an astronomer observes an asteroid, they record its position on the sky at a specific moment in time. Each observation is a single data point. The more data points you collect over a longer period, the more precisely you can calculate the object's orbit. But the orbit is not determined by gravity alone. There are subtle forces at work. Forces so small that they are almost undetectable, yet over years and decades, they can shift an asteroid's path by thousands of kilometers. The most important of these is the Yarkovsky effect, named after the Russian engineer Ein Yarkovsky, who first described it in the early 1900s. The concept is deceptively simple. As an asteroid rotates, the sun heats one side. That side radiates heat, infrared photons, back into space. Those photons carry a tiny amount of momentum. The recoil from that radiation acts as a minuscule thrust, nudging the asteroid in a direction that depends on which way it is spinning. Over a single orbit, the effect is almost nothing. Over decades, it accumulates. Over centuries, it can shift an asteroid's position by millions of kilometers. For Apophis, the Yarkovsky effect was the wild card. Until astronomers could precisely measure how much this thermal thrust was pushing Apophis, they could not reliably predict where it would be in 2029 with the precision needed to rule out the gravitational keyhole. It was like trying to predict where a car would be in 10 years, knowing its speed and direction, but not knowing whether someone had their foot lightly on the gas pedal or the brake. The breakthrough came in March of 2021 during Apophis's close approach at a distance of about 16.8 million kilometers. That is far less dramatic than the 2029 encounter, but it was close enough for radar observations from the Goldstone and Green Bank facilities to measure Apophis's distance and velocity with extraordinary precision. The radar data, combined with optical observations from telescopes around the world, allowed scientists at the Jet Propulsion Laboratory to pin down Apophis's orbit with unprecedented accuracy. The results were definitive. Apophis will not pass through the gravitational keyhole in 2029. It will not return to strike Earth in 2036. In fact, NASA formally removed Apophis from its Century Risk Table, the list of all known objects with a non-zero probability of future impact, for at least the next 100 years. Dave Tholen, one of the co-discoverers, described the moment the calculations were confirmed. When we ran the numbers and saw that the keyhole was excluded, he said, there was a sense of relief that I think only people who had been tracking this object for 17 years could truly feel. We had been carrying this uncertainty for a long time. But here is the problem, the part of the story that the reassuring headlines left out. Apophis was removed from the risk table, yes, but the asteroid is still coming. It is still passing at a distance that is, in every meaningful sense, a near miss, and the 2029 flyby is not just a spectacle. It is a scientific event of the first order, an opportunity and a warning. Because Apophis is not unique, there are thousands of near-Earth asteroids in its size class. Most of them have not been found. Most of them have not been named. And the next one to be discovered might not give us 25 years of warning. It might give us 25 months, or 25 days, or no warning at all. Something is fundamentally incomplete about our ability to protect this planet. Apophis showed us the gap, and in 2029, it will remind us again. The foundation is laid, the discovery has been made, the orbit has been calculated, the threat has been assessed and, for now, dismissed. But this is where the story deepens, because the science of tracking Apophis revealed something far more troubling than any single asteroid. It revealed how much we do not know, how narrow our margins of safety truly are, and how a quirk of celestial mechanics and thermal physics nearly hid a catastrophe from the most powerful telescopes on Earth. But here is what makes this truly terrifying. The story of Apophis is not, at its core, a story about one asteroid. It is a story about a species that lives on a target and has only just begun to realize it. To understand why this matters so profoundly, you need to understand what happened the last time an object, even a fraction of Apophis's size, struck the Earth without warning. On the morning of February 15, 2013, a small asteroid, roughly 20 meters across, about 1/18 the diameter of Apophis, entered the atmosphere above the city of Chelyabinsk, Russia, traveling at approximately 19 kilometers per second. Nobody saw it coming. No telescope detected it. No warning was issued. The rock detonated at an altitude of roughly 29.7 kilometers above the ground, releasing energy equivalent to approximately 500 kilotons of TNT, about 30 times the yield of the Hiroshima bomb. The explosion was an airburst, meaning the asteroid itself largely disintegrated before reaching the surface. But the shockwave was devastating. Over 1,500 people were injured, mostly by flying glass from windows shattered by the blast. Buildings were damaged across a wide area. Dashcam footage from cars across the region captured a fireball brighter than the sun, streaking across the morning sky. followed by a thunderous boom that arrived minutes later. And that was a rock 20 meters across. Apophis is 370 meters across. It is roughly 18 times the diameter of the Chelyabinsk impactor. But here is the critical detail that most people do not intuitively grasp. The energy of an asteroid impact does not scale linearly with size. It scales with the cube of the diameter and the square of the velocity. A rock 18 times wider than the Chelyabinsk object carries vastly more mass, and when you factor in velocity, the energy difference is staggering. The estimated impact energy of Apophis, if it were to strike, is roughly 1,100 megatons. That is more than 2,000 times the energy of the Chelyabinsk event. It is more energy than the combined nuclear arsenals of the United States and Russia detonating simultaneously. This is not science fiction. This is the sober, peer-reviewed calculation published by NASA's Center for Near-Earth Object Studies. Now let us confront the deeper problem that Apophis has forced the scientific community to face: the problem of detection, the problem of uncertainty, and the problem of time. When Apophis was discovered in 2004, the global infrastructure for detecting near-Earth asteroids was, by any honest assessment, woefully incomplete. The primary survey effort at the time was a NASA-funded program called the Space Survey, initiated in 1998, with the goal of finding 90% of near-Earth asteroids 1 kilometer in diameter or larger by the year 2008. That goal was largely achieved. By the late 2000s, astronomers had catalogued the vast majority of the truly civilization-ending asteroids, the ones larger than 1 kilometer, capable of global catastrophe. But there was a critical gap. Objects in the sub-kilometer range, those between 100 and 1,000 meters, were far less well catalogued, and it is precisely this size range that poses the greatest ambiguous threat. An asteroid 1 kilometer or larger would cause a global catastrophe. The threat is existential, the need for detection is obvious, and the political will to fund surveys is relatively easy to muster. An asteroid 10 meters or smaller would produce a brilliant fireball and little else. The damage would be localized and survivable, but an asteroid between 100 and 500 meters, Apophis's size class, sits in a deeply uncomfortable middle zone. It would not end civilization, but it would devastate a region the size of a country. It would kill millions if it struck a populated area. It would trigger economic and social disruption on a scale that the modern world has never experienced. And as of the early 2000s, we had found less than 10% of the objects in this size range. This is the gap that Apophis exposed. Not the gap in our ability to deflect an asteroid, that came later, but the gap in our ability to even know one as coming. The discovery of Apophis was, in a sense, a lucky accident. It was found by a survey team that happened to be looking at the right patch of sky on the right night, using a telescope that was sensitive enough to detect a relatively faint object. If Apophis had been approaching from a slightly different direction, say, from the sunward side, where the glare of the sun blinds our telescopes, it might not have been found until much later, possibly too late for anyone to do anything about it. This is a problem that haunts asteroid scientists. It is called the blind spot problem, and it is terrifyingly real. Ground-based telescopes can only observe the night sky, the hemisphere of space facing away from the sun. Any asteroid approaching from the direction of the sun is invisible to them. It emerges from the glare, crosses the sky, and either misses or hits, and in the latter case, the first warning might be a flash of light and a wall of superheated air. The Chelyabinsk asteroid came from the sunward direction. That is why no one saw it, and Chelyabinsk was a pebble compared to Apophis. In 2005, the United States Congress mandated that NASA find and catalogue 90% of all near-Earth objects 140 meters in diameter or larger by the year 2020. This was called the George E. Brown Jr. Near-Earth Object Survey Act. The deadline was not met. As of 2023, estimates suggest that roughly 40% of the objects in this size range had been found. That means roughly 60% remain undiscovered. 60% of the asteroids large enough to obliterate a city, large enough to trigger continent-wide destruction, large enough to reshape coastlines and darken skies, remain unknown, and it gets worse. Finding an asteroid is only the first step. Calculating its orbit with precision is the second, and the third, and by far the hardest, is determining its exact physical properties, its mass, its density, its spin rate, its thermal characteristics, its composition. All of these factors affect its trajectory over time, and all of them are fiendishly difficult to measure from Earth. Consider the Yarkovsky effect again. For Apophis, astronomers struggled for years to determine whether this tiny thermal thrust was speeding the asteroid up or slowing it down, and by how much. The effect depends on the asteroid's spin direction, its thermal inertia, its albedo, its shape, and its surface roughness. Getting the Yarkovsky acceleration wrong by even a fraction of a billionth of a meter per second squared can translate into a positional uncertainty of thousands of kilometers over a few decades. For an asteroid that passes through a 600-meter-wide keyhole, that kind of uncertainty is the difference between safety and catastrophe. The work that went into resolving the Yarkovsky effect for Apophis is one of the most painstaking achievements in modern astronomy. It required combining optical astrometry, precision measurements of the asteroid's position on the sky, with radar range and Doppler measurements, thermal modeling of the asteroid's surface, and sophisticated numerical integration of its orbit through the gravitational fields of every major body in the solar system. The team at the Jet Propulsion Laboratory, led by scientists including Davide Farnocchia, spent years refining this analysis. The breakthrough paper, published in 2021 after the radar campaign, concluded that the Yarkovsky drift for Apophis was accelerating its orbital motion by approximately negative 170.3 plus or minus 43 meters per year. That number, negative 170 meters per year, represents the accumulated shift in Apophis's along-track position due to the Yarkovsky effect. Over a decade, it amounts to about 1.7 kilometers. Over a century, far more. And knowing that number with confidence was the key to ruling out the 2036 impact scenario. But here is the problem that persists. We do not have Yarkovsky measurements for most near-Earth asteroids. We do not have radar data for most of them. We do not have shape models or spin state determinations for most of them. For the overwhelming majority of the potentially hazardous asteroids we have catalogued, we know their orbits to a useful but imperfect degree of accuracy, and we know almost nothing about the subtle forces that will shape their trajectories over the coming centuries. This means that our risk assessments are built on incomplete foundations. When NASA says an asteroid has a 1 in 10,000 chance of impact, that number is derived from an orbit that may not account for the Yarkovsky effect or the Yorp effect, a related torque that changes an asteroid's spin rate over time, or gravitational perturbations from unmodeled encounters with other asteroids. The error bars are large, and for some objects, they are large enough to hide a future impact. Let us talk about another dimension of this problem, the problem of what happens after detection. Because even if we find every asteroid, even if we calculate every orbit to perfection, we still face the question that Apophis first forced the world to ask: what do we do about it? In 2004, when the impact probability for Apophis briefly reached 2.7%, there was no plan. There was no technology ready to deflect it. There was no international framework for deciding who would act, how they would act, or who would authorize the action. The world's space agencies had conducted studies, published papers, and held conferences. But there was no hardware, no mission architecture, no tested capability. If Apophis had been on a collision course, humanity would have had 25 years of warning, and, at the time, essentially zero ability to respond. This realization was deeply disturbing to the scientists involved. Rusty Schweickart, the Apollo 9 astronaut, who became one of the leading advocates for planetary defense, described the situation bluntly in a speech to the Association of Space Explorers. "We have the technology to deflect an asteroid. We do not have the technology ready. There is a difference, and that difference could be measured in millions of lives." The distinction Schweickart drew is critical. Deflecting an asteroid is not conceptually difficult. The physics is well understood. If you can change the velocity of an incoming asteroid by even a fraction of a centimeter per second, and you do it early enough, years or decades before the predicted impact, the accumulated change in position will be enough to turn a direct hit into a clean miss. The methods that have been proposed are varied and range from the elegant to the brutal. A kinetic impactor, essentially a spacecraft that rams the asteroid at high speed, transfers momentum and nudges the orbit. A gravity tractor, a spacecraft that hovers near the asteroid for years, using its own gravitational pull to slowly tug the orbit, is gentler but requires more time. Ion beam deflection, laser ablation, and even nuclear standoff detonation have been studied. The physics works, the engineering is plausible, but none of these methods had been tested when Apophis was discovered. Not a single one had been demonstrated on an actual asteroid. The gap between theory and capability was enormous. This gap is what makes the Apophis story so unsettling. It is not the asteroid itself. We know it will miss in 2029. It is what the asteroid revealed about us. We were, and to a significant degree still are, a civilization that can identify a threat from space, calculate its probability of impact, publish the results in peer-reviewed journals, and then do almost nothing about it. Let us talk about the timeline, because it matters. From the moment Apophis was discovered in June of 2004 to the moment its impact in 2029 was definitively ruled out, a process that unfolded in stages over the following months. The world was in a state of genuine, if quiet, alarm. The initial orbit, calculated from just 2 nights of observation, carried massive uncertainty. It was enough to flag the object for follow-up, but not enough to determine whether it posed a threat. When additional observations refined the orbit in December of 2004, the impact probability shot upward. On Christmas Eve of 2004, a date that many asteroid scientists remember vividly, the probability reached its peak of approximately 2.7%. The news leaked to the public in fragments. Some media outlets reported the threat responsibly, others sensationalized it. The scientific community was divided on how to communicate the risk. Should the public be told about a 2.7% chance of a catastrophic impact 25 years in the future? Or would the disclosure cause unnecessary panic? The debate raged inside the asteroid research community, and it exposed a problem that remains unresolved to this day. There is no globally agreed upon protocol for communicating asteroid threats to the public. Each nation, each space agency, each observatory makes its own judgment call. The result is a patchwork of statements, press releases, and media coverage that varies wildly in accuracy and tone. In the end, additional observations, crucially, pre-discovery images of Apophis found in archival data from the Spacewatch survey, extended the observational arc and dramatically shrank the uncertainty. By late December of 2004, the impact probability for 2029 dropped to less than 1 in 45,000. By subsequent years, it was effectively zero, but the scare had left its mark. That Christmas was the moment I realized we were not ready, said Steve Chesley, a senior scientist at the Jet Propulsion Laboratory, who was deeply involved in the Apophis risk assessment. We had identified a credible threat, and our response was to observe it more carefully and hope the numbers got better. That is not a defense strategy, that is luck. There is another layer to this problem, and it is perhaps the most psychologically difficult to confront. It is the problem of human bias in the face of low probability, high consequence events. Apophis taught us something about ourselves, something uncomfortable. When the impact probability was 2.7%, most people heard 97.3% chance it will miss and stopped worrying. That is a natural human response. Our brains are wired to discount unlikely events. But consider what 2.7% actually means. If someone handed you a revolver with 37 chambers and told you that one of them held a live round and then pointed it at the city you live in and pulled the trigger, would you consider that an acceptable risk? That is the scale of what Apophis represented. A 1 in 37 chance of a 1,000 megaton impact on a populated planet. And the response was, for the most part, to wait for more data. Now, to be fair, waiting for more data was the scientifically correct response. The initial orbit was uncertain, and more observations were needed to refine it. That is how science works. But the deeper question is, what would have happened if the observations had not brought relief? What if the additional data had confirmed the threat instead of eliminating it? What mission would have been launched? What spacecraft was sitting on a launch pad, ready to go? The answer in 2004 was none. The problem extends beyond hardware. It extends to the fundamental geometry of asteroid detection. Most asteroid surveys use ground-based optical telescopes that scan the night sky. These telescopes are extraordinarily powerful, but they share a fundamental limitation. They can only see objects that are illuminated by the sun and positioned against the dark background of space. An asteroid approaching from the daytime sky, from the direction of the sun, is effectively invisible. It is washed out by solar glare. And this is not an edge case. A significant fraction of potentially hazardous asteroids approach Earth from the sunward direction at some point during their orbits. The solution that NASA and the European Space Agency have pursued is a space-based infrared telescope, a satellite that would orbit the sun and scan for asteroids by detecting the heat they emit, regardless of the direction of sunlight. This concept has been in development for years under various names. The Near-Earth Object Surveyor, or NEO surveyor, is NASA's current incarnation. It is designed to find 90% of potentially hazardous asteroids 140 meters or larger within a decade of launch. It was approved for development. It has been funded, defunded, delayed, refunded, and rescheduled multiple times. As of the mid-2020s, it is expected to launch, but the timeline has slipped repeatedly. The story of NEO Surveyor is, in miniature, the story of humanity's approach to planetary defense. We understand the threat, we design a solution, and then we struggle to fund and deploy it with the urgency it deserves. The asteroid does not care about our budget cycles. It does not wait for congressional approval. It follows the laws of celestial mechanics with perfect indifference to human politics. And this brings us to the event that, perhaps more than any other, illustrates both the promise and the frustration of planetary defense. In September of 2022, 18 years after Apophis was discovered and 7 years before its close approach, NASA launched a mission called DART, the Double Asteroid Redirection Test. Its target was not Apophis. It was a small moonlet called Dimorphos, orbiting a larger asteroid called Didymos. The mission's goal was simple and historic. Ram a spacecraft into Dimorphos at roughly 6.1 kilometers per second and measure how much the impact changed the moonlet's orbit. On September 26, 2022, the DART spacecraft struck Dimorphos. The impact was captured by cameras on the spacecraft itself and by a small Italian CubeSat called LissiaCube that had deployed from DART 15 days earlier. The images were stunning, a field of boulders filling the frame as the spacecraft hurtled toward the surface, then blackness as the signal ended. The impact was successful. Dimorphos's orbital period, the time it takes to orbit Didymos, was shortened by approximately 32 minutes. The mission had aimed for a change of at least 73 seconds. The actual change was more than 25 times that expectation. The scientific community celebrated. It was a genuine milestone, the first time humanity had deliberately altered the orbit of a celestial body. But the celebration was tempered by a critical caveat. DART was a test. It was not a defense. Dimorphos was chosen precisely because it posed no threat to Earth. The change in its orbit affected only its path around Didymos, not the Didymos system's trajectory through the solar system, and the mission revealed complexities that had not been fully anticipated. The amount of ejecta thrown off by the impact was far greater than expected, meaning the momentum transfer was dominated by the recoil from debris, not the direct impact of the spacecraft itself. This made the result more effective, but also less predictable. If we ever need to deflect a real threat, the uncertainty in the outcome could be the difference between a near miss and a direct hit. But here is the problem. The DART mission took years to develop, build, and launch. From initial concept to impact, the timeline was roughly a decade. If a threatening asteroid were discovered tomorrow, an object of Apophis's size, on a collision course with Earth in 5 years, there is no kinetic impactor sitting in a warehouse ready to launch. There is no gravity tractor. There is no nuclear deflection mission on standby. The global planetary defense infrastructure, as of today, consists of detection and tracking. The response capability is, at best, in its infancy, and the universe does not wait for us to be ready. Let us return to Apophis itself and confront the full scope of what the 2029 flyby means for our understanding of our own vulnerability. When Apophis passes at 31,860 kilometers on April 13th, 2029, Earth's gravity will wrench its orbit into a new shape. The orbital period will change, the inclination will change, the eccentricity will change. The asteroid that arrives will leave as a different dynamical object. And while the next 100 years of its new orbit have been analyzed and declared safe, the longer-term future is inherently uncertain. Orbital dynamics is a chaotic system. Small perturbations, a close pass by another asteroid, an unmeasured Yarkovsky drift, a gravitational interaction during a distant planetary encounter can compound over time into large positional uncertainties. Predicting where Apophis will be in 50 years is possible with high confidence. Predicting where it will be in 500 years is not. The mathematics of chaos guarantee that beyond a certain time horizon, the trajectory of every asteroid in the solar system becomes fundamentally unpredictable. So when scientists say Apophis will not hit Earth in the next 100 years, they are telling the truth. But they are also drawing a line at the edge of what the math can reliably deliver. Beyond that line is darkness, not metaphorical darkness, but genuine mathematical uncertainty. The orbit of Apophis after 2029 will be reshaped by forces we can model but cannot perfectly predict. And in that uncertainty, there is always the possibility of a future close encounter that we cannot yet foresee. This is the core problem. It is not Apophis. It is the nature of the solar system itself. We live in a gravitational shooting gallery where the bullets are invisible, the trajectories are chaotic, and our ability to detect, track, and respond is improving, but slowly and against the backdrop of a cosmic timescale that does not care about our progress. But here is what makes this truly terrifying. The next Apophis might already be out there, orbiting in the blind spot between the Sun and the Earth, waiting for geometry and gravity to align. And there is one more piece of this puzzle that demands attention before we move deeper into the investigation. A piece that connects the story of Apophis to the oldest scars on Earth itself. Because Apophis is not an anomaly, it is not a freak occurrence. Objects like Apophis have been striking Earth for 4.5 billion years, and the evidence is written in stone, literally, in craters that dot every continent and every ocean floor on the planet. Consider Meteor Crater in Arizona, also known as Barringer Crater. It is 1.2 kilometers across and 170 meters deep, carved into the desert floor by an iron asteroid roughly 50 meters in diameter that struck approximately 50,000 years ago. 50 meters. That is roughly 1/7 the size of Apophis. The energy released was equivalent to about 10 megatons of TNT, enough to flatten everything within a radius of several kilometers. If the same object struck a modern city today, the death toll would be in the hundreds of thousands. Now scale that up. The Chicxulub crater, buried beneath the Yucatan Peninsula in Mexico, is 180 kilometers across. It was created 66 million years ago by an asteroid roughly 10 to 15 kilometers in diameter, an object 40 times the size of Apophis. The impact released energy equivalent to roughly 100 trillion tons of TNT, triggered global wildfires, sent a curtain of dust and sulfur into the stratosphere that blocked sunlight for months, collapsed food chains on land and in the oceans, and ended the reign of the dinosaurs. 75% of all species on Earth went extinct. Apophis would not cause a Chicxulub-level event. It is far too small for that. But it would cause devastation on a scale that no living human has ever witnessed. The energy of 1,000 megaton impact is difficult to visualize, so let us try. Imagine the most powerful nuclear weapon ever tested. The Soviet Tsar bomber detonated on October 30th, 1961, with a yield of approximately 50 megatons. It shattered windows over 900 kilometers away. Its mushroom cloud rose 67 kilometers into the sky. The flash of light was visible from 1,000 kilometers. Now imagine an explosion 22 times more powerful than that. Not in the controlled conditions of a test site, but slamming into a populated region at cosmic velocity, converting kinetic energy into thermal radiation, seismic waves, and a superheated plume of vaporized rock and atmosphere. The impact simulations, run by researchers at Imperial College London and Purdue University, using a tool called the Earth Impact Effects Program, paint a grim picture. A 370-meter iron and silicate asteroid striking land at 31 kilometers per second would create a crater roughly 5 to 6 kilometers in diameter. The air blast would flatten buildings within a radius of tens of kilometers. Thermal radiation would cause severe burns at distances of up to 50 kilometers from the impact site. Seismic shaking equivalent to a magnitude 7 earthquake would be felt for hundreds of kilometers. Ejecta, chunks of rock hurled into the atmosphere by the impact, would rain down across a region the size of a small country. If the impact occurred in an ocean, the resulting tsunami could reach heights of tens of meters at coastlines hundreds of kilometers from the strike point. And all of this from an object you could walk across in about 4 minutes. This is the reality that Apophis has forced the scientific community to confront with renewed urgency. The threat is not theoretical, it is statistical. Objects in Apophis's size range strike the Earth, on average, once every 80,000 years or so. That average is misleading because asteroid impacts are not evenly spaced. They are random events governed by orbital mechanics and gravitational perturbations. The next one could happen in 50,000 years. It could happen in 500. The only certainty is that it will happen, given enough time. The question is not whether Earth will be struck again by an object of this size. The question is whether we will see it coming, and whether, when we do, we will have the means and the will to stop it. This is what kept the scientists who tracked Apophis awake at night, not the asteroid itself. They had calculated that it would miss. But the knowledge that the next Apophis might not be found by a survey telescope on a clear night in Arizona. It might be found by an infrared satellite that has not yet been launched, or by a telescope that has not yet been built, or, worst of all, by the flash of light above a city that had no warning at all. The timeline of human awareness is vanishingly short. For billions of years, asteroids struck Earth with no one to notice. For thousands of years, humans looked up at meteors and shooting stars and called them omens or divine messages, having no concept of their true nature. It was only in the early 1900s that scientists began to seriously study impact craters. It was only in the 1980s, after the Alvarez hypothesis linked the Chicxulub impact to the extinction of the dinosaurs, that the scientific mainstream accepted that asteroid impacts were a real and recurring threat. And it was only in the 1990s that the first systematic surveys to find near-Earth asteroids were funded and deployed. We have been seriously looking for the objects that could destroy us for roughly 3 decades. The solar system has been throwing them at us for 4.5 billion years. The mismatch is staggering. And yet, within those 3 decades, enormous progress has been made. The Catalina Sky Survey, based in Arizona, has discovered more near-Earth asteroids than any other program. The Pan-STARRS telescope system in Hawaii scans the sky nightly, cataloguing new objects and refining orbits of known ones. The ATLAS system, the Asteroid Terrestrial Impact Last Alert System, operates telescopes in Hawaii, Chile, South Africa, and the Canary Islands, providing near-complete coverage of the accessible night sky with the specific goal of detecting approaching asteroids days to weeks before a potential impact. And the forthcoming Vera-C, Rubin Observatory in Chile, with its 8.4-meter mirror and 3.2 gigapixel camera, is expected to revolutionize asteroid detection when it begins its 10-year survey of the southern sky. These are real achievements, built by real scientists working within the constraints of real budgets. But the constraints are severe. Planetary defense competes for funding with every other scientific priority: climate research, medical research, space exploration, fundamental physics. The annual budget for NASA's Planetary Defense Coordination Office is measured in hundreds of millions of dollars, a substantial sum in absolute terms, but a rounding error in the context of the federal budget, and a fraction of what is spent on any single major defense program. The irony is almost too neat. Humanity spends trillions of dollars each year defending against threats from other humans, missiles, armies, cyber attacks. It spends a fraction of a % of that amount defending against a threat that, given enough time, is mathematically certain: an asteroid impact of catastrophic proportions. The dinosaurs did not have a space program. We do. Whether we use it in time is, as of tonight, an open question. There is a subtlety here that deserves attention because it reveals something about the nature of the threat that even many scientists did not fully appreciate until the Apophis scare forced a reckoning. It is the problem of what happens in the hours and days after an impact is predicted. Not the physical impact, but the social and political one. When Apophis reached its peak probability of 2.7% on Christmas Eve of 2004, there was no established chain of command for responding to an asteroid threat. There was no hotline between NASA and the United Nations. There was no pre-drafted message template for informing world leaders. There was no agreed-upon procedure for telling the public that a mountain-sized rock had a measurable chance of striking their planet within their lifetimes. The scientists who computed the probability were, in many cases, the same people who had to decide whether and how to announce it. This created a chaotic information environment. Some researchers posted the preliminary data on public mailing lists, triggering sensational media coverage before the calculations were confirmed. Others argued for withholding the information until the orbit was better constrained. The debate exposed a fundamental tension in the science of asteroid threats. Transparency demands that the public be informed of risks as they are discovered, but incomplete data can cause disproportionate panic. A 2.7% chance of impact, announced on Christmas Eve, became a worldwide news story. When subsequent observations reduced that probability to near zero within weeks, the retraction received a fraction of the attention. The result was a loss of credibility that planetary defense scientists have spent years trying to repair. If the public perceives asteroid threats as a series of false alarms, objects that were supposedly dangerous but turned out to be harmless, the response to a future genuine threat may be fatally delayed by skepticism. The boy who cried wolf problem is not an abstraction in planetary defense. It is a strategic vulnerability. In response to the Apophis experience, the International Astronomical Union established the Minor Planet Center as the formal clearinghouse for asteroid observations and orbit calculations. NASA created the Planetary Defense Coordination Office in 2016, centralizing threat assessment and communication under one organizational roof. The United Nations Committee on the Peaceful Uses of Outer Space established the International Asteroid Warning Network and the Space Mission Planning Advisory Group, providing at least the skeleton of a global coordination framework. But these are frameworks, not capabilities. They are protocols for communication, not for action. When the next Apophis is found, an object of similar size, on a trajectory that does not conveniently resolve into a miss, the communication will flow through proper channels. The press releases will be carefully worded. The risk will be assessed by qualified teams. But the question that matters, can we stop it, will still depend on whether anyone has built, tested, and deployed the hardware needed to push a rock out of the way. As of tonight, the answer is, we are closer than we were, but we are not there yet. This is the uncomfortable truth that Apophis has written across the sky in letters that most of the world has yet to read. We live on a planet that sits in the path of objects large enough to reshape continents, and we have only just begun to take that fact seriously. The infrastructure is growing. The knowledge is deepening. The political will is forming, slowly, grudgingly, in fits and starts. But the clock is ticking with the steady, implacable rhythm of orbital mechanics, and the asteroids do not negotiate. And yet, for all the institutional progress, for all the surveys and protocols and advisory groups, the single most important lesson of Apophis is one that resists being reduced to a policy recommendation or a budget line item. It is a lesson about human perception, about the gap between what we know and what we feel, between what the numbers say and what we are willing to act on. Consider this thought experiment. If a team of geologists announced that a major earthquake would strike a specific city within the next 25 years with a 2.7% probability, that city would immediately begin reinforcing its buildings, updating its emergency plans, and stockpiling disaster relief supplies. A 2.7% chance of a devastating earthquake would be treated as an urgent, actionable threat. Billions of dollars would be mobilized. Political careers would be built on preparedness. But when astronomers announced a 2.7% chance of a devastating asteroid impact, an event potentially thousands of times more energetic than any earthquake, the response was muted, intrigued, briefly alarmed, and then, when the probability dropped, relieved and forgetful. The asteroid was no longer on a collision course, so the problem was filed away. The underlying vulnerability, the fact that the next discovery might not come with such a convenient resolution, was quietly shelved. This is not a failure of science. It is a failure of imagination. The human brain evolved to respond to threats that are immediate, visible, and personal. A predator in the grass, a storm on the horizon, a rival tribe across the river. An asteroid is none of these things. It is distant, invisible, impersonal. It does not growl. It does not flash lightning. It does not carry a weapon. It simply follows the curve of space-time in perfect mathematical silence, and either misses or does not. There is no negotiation, no warning shot, no opportunity for diplomacy. There is only the orbit, and whether we happen to be standing in its way. Apophis has given humanity something extraordinary, a preview, a rehearsal, a dress rehearsal for the day when the math does not break in our favour. In 2029, when that point of light drifts across the evening sky, every person who looks up will be witnessing the closest approach of an asteroid this size in the history of human civilization. They will be seeing, with their own eyes, what the dinosaurs never saw. The kind of object that, given a slightly different set of initial conditions, could rewrite the future of life on Earth. The question is whether we will treat that moment as a spectacle or as a warning, whether we will watch it pass and return to our lives, or whether we will look at that fading point of light and understand what it means. Not just what it means for the science of orbital mechanics or the engineering of planetary defense, but what it means for a species that has, for the first time in 4.5 billion years of terrestrial life, the ability to see the threat coming and the potential to do something about it. That ability is new, it is fragile, and it is not yet sufficient. The foundation has been laid, the discovery has been made, the orbit has been calculated with exquisite precision. The threat for 2029 has been resolved, but the deeper problem, the problem of all the asteroids we have not yet found, the problem of all the missions we have not yet flown, the problem of a civilization that knows its own vulnerability but has not yet fully committed to addressing it, that problem remains wide open. And as we move deeper into this story, we are going to follow the scientists who took the lesson of Apophis and tried to turn it into action. We are going to follow the missions, the telescopes, the theories, and the arguments. We are going to see what humanity has done and what it has failed to do in the years since a rock named after the Egyptian god of chaos first appeared on a screen in Arizona and changed everything. Because what scientists discovered next, when they began to truly examine what the 2029 flyby would do to Apophis, and what Apophis could teach us about the invisible population of near-Earth objects lurking in our cosmic neighborhood, was worse than anyone expected. The reassurance that Apophis would miss was real, but the reassurance came with a caveat that most headlines never mentioned. The close pass would transform Apophis, physically, dynamically, and in ways that would make its future trajectory harder to predict, not easier. The encounter with Earth's gravity would not simply bend its orbit and send it on its way. It would shake the asteroid to its core, potentially altering its spin, its shape, and its surface in ways that no telescope on Earth could fully anticipate. The 2029 flyby is not just a close call. It is a natural experiment, one that nature is running whether we are ready to observe it or not. And the scientists who recognized this began to plan for it with a mixture of excitement and urgency that had not been seen in the planetary science community since the discovery of Apophis itself, because they understood something that the public did not. This would be humanity's single best opportunity to study a potentially hazardous asteroid up close, in real time, during an event that could never be replicated. Miss it, and we would have to wait generations for another chance. The clock was ticking, and the missions were just beginning to take shape. The race between scientific ambition and the unyielding calendar of celestial mechanics would produce some of the most audacious space mission proposals in a generation. Some would be approved, some would be cancelled, and some would reveal truths about Apophis that made the original scare of 2004 seem almost quaint by comparison. The discovery of Apophis did not just reveal a threatening asteroid. It triggered a cascade of scientific, engineering, and political responses that would unfold over the next 2 decades, each one an attempt to answer a different facet of the same question. What should humanity do when it finds a rock with its name on it? The first of these responses was, in many ways, the most straightforward and the most frustrating. It was the attempt to observe Apophis more precisely from the ground, and it began almost immediately after the December 2004 scare. The problem was deceptively simple: to predict where Apophis would be in 2029 with the precision needed to rule out a collision. Astronomers needed more observations. Each observation, a measurement of the asteroid's position on the sky at a specific time, added a data point to the orbital solution. The more data points, spread over a longer time, the narrower the uncertainty in the orbit. In principle, this is routine. Asteroid observers do it every night. But Apophis was not a routine case. Its orbit brought it close to Earth only at specific intervals, and between those close approaches, it was far away, faint, and difficult to observe. After the December 2004 scare, Apophis became the most observed asteroid in history. Telescopes around the world tracked it obsessively. The Arecibo Observatory in Puerto Rico, with its massive 305-meter radio dish, was turned on Apophis during its 2005 and 2006 apparitions, bouncing radar signals off the asteroid's surface and measuring the return signal to determine its distance and velocity with millimeter-per-second precision. Those radar observations were critical. Optical telescopes measure an asteroid's position on the sky, its angular coordinates, but they cannot directly measure its distance. Radar does both. A radar observation pins down the asteroid's 3-dimensional position in space, which is far more valuable for orbit determination than an optical observation alone. The Arecibo data from 2005 reduced the uncertainty in Apophis's predicted position in 2029 by a factor of several hundred, but Arecibo was not available for the most critical observation window. In August of 2020, the observatory suffered a catastrophic structural failure. One of the support cables holding the 900-ton instrument platform above the dish snapped, crashing into the dish below and tearing a 30-meter gash in the reflector surface. A second cable failed 3 months later. On December 1, 2020, the entire instrument platform collapsed, destroying the telescope beyond repair. The loss of Arecibo was a blow to planetary defense that extends far beyond Apophis. For decades, it had been the most powerful planetary radar system in the world, capable of detecting and characterizing asteroids at distances that no other facility could match. Its destruction left the Goldstone Solar System radar, operated by NASA's Jet Propulsion Laboratory, using a 70-meter antenna in the Mojave Desert, as the only fully operational planetary radar in the United States. Goldstone is powerful, but its antenna is smaller than Arecibo's, giving it less sensitivity. The loss was felt immediately in the Apophis campaign. Fortunately, the March 2021 close approach of Apophis, at a distance of roughly 16.8 million kilometers, was close enough for Goldstone to obtain excellent radar data even without Arecibo. The Goldstone team, supplemented by receiving support from the Green Bank Telescope in West Virginia, spent several days bouncing radar pulses off Apophis and capturing the faint echoes. The resulting data allowed them to measure the Yarkovsky effect on Apophis's orbit for the first time and to definitively rule out the 2036 impact scenario. It was a triumph of precision measurement and a reminder of how dependent planetary defense is on a handful of aging, irreplaceable facilities. The radar campaign also produced the best-shaped model of Apophis to date, revealing its bilobed structure and confirming that it tumbles as it rotates. This information is not merely academic. If we ever need to deflect an asteroid like Apophis, knowing its shape, mass distribution, and spin state is essential for designing a kinetic impactor mission. A spacecraft aimed at the wrong part of a tumbling, bilobed asteroid might transfer momentum in the wrong direction or shatter the asteroid into fragments that still threaten Earth. The Goldstone observations showed that Apophis, while not a rubble pile, is also not a monolith. It has internal structure, and any deflection attempt would need to account for that. Now, let us turn to the second major response to Apophis, the one that moved from observation to action. This was the birth of the DART mission, and it is a story worth telling in full, because it represents humanity's first real step toward defending itself against the threat that Apophis embodies. The idea of a kinetic impactor test had been discussed in the planetary defense community for years before Apophis was discovered. The concept is almost absurdly simple. Hit the asteroid with a spacecraft. The spacecraft does not need to carry a weapon or an explosive. Its own mass, traveling at several kilometers per second, delivers enough momentum to alter the asteroid's velocity by a small but measurable amount. If you do this years or decades before a predicted impact, the accumulated orbital change turns a direct hit into a miss. The physics was well understood, the engineering was plausible, but no one had ever actually tried it. And without a test, no one could be confident that the models were correct. How much ejector would the impact produce? How much momentum would that ejector carry away? Would the asteroid absorb the impact like a pillow, or shatter like glass, or something in between? These questions could not be answered by computer simulations alone. They required a real experiment on a real asteroid. The DART mission, Double Asteroid Redirection Test, was proposed by a team at the Johns Hopkins Applied Physics Laboratory and formally approved by NASA in 2018. Its target was carefully chosen, Dimorphos, a small moonlet roughly 160 meters in diameter, orbiting a larger asteroid called Didymos. The binary system was ideal for a test because the impact's effect on Dimorphos's orbit around Didymos could be measured from Earth using ground-based telescopes. If the spacecraft shortened Dimorphos's orbital period, the change would be detected as a shift in the timing of mutual eclipses and occultations between the two bodies. No need to track a subtle change in the asteroid's heliocentric orbit, just measure the clock. DART launched on November 24, 2021, from Vandenberg Space Force Base in California, aboard a SpaceX Falcon 9 rocket. It carried a single instrument, Draco, a high-resolution camera, that would guide the spacecraft to its target using autonomous navigation. There was no backup, no abort option. The spacecraft was designed to hit Dimorphos at roughly 6.1 kilometers per second and be destroyed on impact. 10 months later, on September 26, 2022, the world watched live as DART's camera transmitted its final images. In the last minutes, the feed showed a field of stars resolving into a small bright point, Didymos. Then, as the spacecraft drew closer, a smaller point emerged beside it, Dimorphos. The resolution sharpened with every frame. Individual boulders became visible on the surface. The moonlet filled the screen, and then blackness. The signal was gone. DART had struck its target. The impact was confirmed within seconds by LissiaCube, a small Italian CubeSat that had separated from DART 2 weeks earlier, and flew past the impact site minutes after the collision, capturing images of the expanding plume of debris. Ground-based telescopes around the world trained their instruments on the Didymos system and began timing the eclipses. Within days, the result was clear. Dimorphos's orbital period had been shortened by approximately 32 minutes, from 11 hours and 55 minutes to 11 hours and 23 minutes. The numbers are striking. The DART spacecraft weighed roughly 570 kilograms, about the mass of a large motorcycle. Dimorphos weighs roughly 4.3 billion kilograms. The ratio is absurd. It is like a mosquito changing the course of a freight train. And yet, it worked. The momentum transfer was enhanced by a factor of roughly 3.6 by the ejector. The debris blasted off the surface by the impact carried away more momentum than the spacecraft itself. Delivered. The recoil from that debris plume was the dominant contributor to the orbital change. This was both encouraging and sobering. Encouraging because the effect was far larger than the minimum needed. Sobering because the enhancement factor was highly dependent on the properties of Dimorphos's surface, its porosity, its strength, its composition, and those properties varied across the moonlet's surface. A different impact location, a different angle, a different surface type could have produced a very different result. For a real deflection mission, where the margin of error might be measured in meters, this uncertainty could be critical. The European Space Agency recognized this and designed a follow-up mission called Hera, which launched in October of 2024, bound for the Didymos system, to conduct a detailed post-impact survey. Hera carries 2 CubeSats and a suite of instruments designed to measure Dimorphos's mass, internal structure, surface properties, and the precise shape of the impact crater left by DART. The data from Hera will close the loop on the DART experiment, transforming it from a spectacular demonstration into a calibrated tool, one that could be used with confidence in a future emergency. But here is the uncomfortable truth that the DART success cannot conceal. The test was conducted under ideal conditions. The target was known. Its orbit was well characterized. There was no time pressure. The mission had years to plan, build, and launch. In a real deflection scenario, an Apophis-class asteroid discovered on a collision course with 5 or 10 years of warning, every one of those advantages disappears. The target's mass and composition would be uncertain. The time available for mission development would be compressed. The margin for error would be razor-thin. And there is a darker scenario still, one that planetary defense scientists discuss in closed sessions, but rarely in public. What if the warning time is not years, but months? What if a large asteroid is discovered on a short arc trajectory, emerging from the sun blind spot, and the impact is predicted for less than a year from the date of discovery? In that case, a kinetic impactor is useless. There is not enough time to build, launch, and fly a spacecraft to the target. The only option that has been seriously studied for short warning scenarios is a nuclear standoff detonation. Detonating a nuclear weapon at a distance from the asteroid's surface, using the intense burst of X-rays and neutrons to vaporize a layer of the surface and produce a rocket-like thrust in the opposite direction. This approach has been modeled extensively in computer simulations by researchers at Lawrence Livermore National Laboratory and the Los Alamos National Laboratory. The physics is well established. A nuclear device detonated at the optimal standoff distance from an asteroid would produce a velocity change significantly larger than a kinetic impactor of any feasible mass. It is, by a wide margin, the most effective deflection method available for short warning, large asteroid scenarios. But it has never been tested. It has never been approved for use. And it exists in a political and legal limbo that makes deployment extraordinarily difficult. The Outer Space Treaty of 1967 prohibits the placement of nuclear weapons in space. While legal scholars have argued that a one-time emergency deflection mission would not violate the treaty's intent, the political reality is that any nation proposing to launch a nuclear weapon into space, even to save the planet, would face intense international scrutiny, legal challenges, and the risk of geopolitical miscalculation. A nuclear deflection mission would require a level of international cooperation and trust that frankly does not currently exist. The third major response to Apophis was the effort to build a dedicated space-based telescope for finding near-Earth asteroids. And this story is, in many ways, the most frustrating of all because it illustrates the agonizing gap between recognizing a threat and actually doing something about it. The concept of a space-based infrared asteroid hunter dates back to the early 2000s. Ground-based optical telescopes have a fundamental limitation. They detect asteroids by the sunlight they reflect. Small dark asteroids, those with low albedo, reflect very little light and are therefore difficult to find. But every asteroid, regardless of its albedo, emits thermal infrared radiation simply because it absorbs sunlight and re-emits it as heat. An infrared telescope in space, shielded from the glare and thermal noise of Earth's atmosphere, could detect asteroids by their heat signatures, finding dark objects that optical surveys miss, and providing direct measurements of their sizes. NASA's first attempt at such a mission was called NEOCAM, the Near-Earth Object Camera. It was proposed in 2006, shortly after the Apophis scare. It went through NASA's competitive mission selection process, reaching the final round of consideration multiple times, in 2010, in 2015, and in 2017. Each time, it was passed over in favor of other missions. The planetary science community watched in mounting frustration as the concept was repeatedly studied, praised, deferred, and resubmitted. In 2019, NASA finally committed to a version of the mission under a new name, NEO-Surveyor. It was assigned to a dedicated budget line within the Planetary Defense Coordination Office, insulating it from the competitive selection process that had delayed it for over a decade. The mission is designed to operate at the Sun-Earth Lagrange point L1, scanning the sky in 2 infrared wavelengths, optimized for detecting the thermal emission of near-Earth asteroids. Its goal is to find 90% of potentially hazardous asteroids, 140 meters, and larger within 5 years of beginning survey operations, and to contribute to the catalogue of smaller objects as well. But the road from approval to launch has been anything but smooth. Budget constraints, technical challenges, and the disruptions of global events have pushed the launch date back repeatedly. The most recent estimates place the launch in the late 2020s, meaning it may or may not be operational before Apophis makes its close pass in April of 2029. The irony is thick. The asteroid that demonstrated the urgent need for a space-based detection system may arrive before the system designed to detect objects like it is in place. The fourth response, and perhaps the most scientifically ambitious, is the plan to study Apophis itself during the 2029 flyby. This is where the story shifts from defense to science, and it is a story that deserves its own chapter. In April of 2029, Apophis will be closer to Earth than any asteroid of its size has been in recorded history. For planetary scientists, this is not a threat. It is a gift. It is an opportunity to study a potentially hazardous asteroid at a distance where telescopes, radar, and even small spacecraft can examine it in exquisite detail. And the scientific community is preparing for it with an intensity that borders on obsession. The most prominent mission in this effort is OSIRIS-APEX, a repurposed NASA spacecraft originally built as OSIRIS-REx, which successfully collected a sample from the asteroid Bennu and returned it to Earth in September of 2023. After dropping off the Bennu sample capsule, the spacecraft still had fuel, functioning instruments, and a perfectly good trajectory. NASA decided to redirect it toward Apophis, renaming it OSIRIS-APEX. Origins, spectral interpretation, resource identification, and security. Apophis Explorer. OSIRIS-APEX is scheduled to rendezvous with Apophis roughly 1 month after the 2029 Earth flyby, and will spend at least 18 months studying the asteroid from close range. Its instruments will map the surface in visible and infrared wavelengths, measure the composition, and, critically, document the changes that the Earth encounter produces. Because this is the part of the 2029 flyby that most people do not realize. When Apophis passes through Earth's gravitational field at 31,860 kilometers, the tidal forces exerted on the asteroid will be enormous. Earth's gravity will not just bend Apophis's orbit, it will physically stress the asteroid. Tidal forces, the differential gravitational pull on the near and far sides of the asteroid, will stretch and squeeze the rock, potentially triggering landslides, exposing fresh surface material, changing the spin rate, and possibly even altering the asteroid's internal structure. The asteroid will emerge from the encounter physically different from the one that entered it, and OSIRIS-APEX will be there to document every change. This is unprecedented. No spacecraft has ever observed an asteroid undergoing tidal disruption in real time. The data will inform every future assessment of how potentially hazardous asteroids respond to gravitational stress, how their surfaces evolve, and how their spin states change. It will also provide a direct, close-range measurement of the Yarkovsky effect on a well-characterized body. The first time this has been done for an asteroid of Apophis's size class. But OSIRIS-APEX is not the only mission being planned. In the years leading up to 2029, multiple space agencies and private entities have proposed missions to Apophis. Some are small, CubeSats that would fly past during the close approach and image the asteroid in its moment of closest passage. Others are more ambitious, proposed landers or impactors designed to study the asteroid's surface or interior. The European Space Agency has discussed possible flyby missions. The Japan Aerospace Exploration Agency, JAXA, the agency behind the Hayabusa missions that successfully sampled 2 asteroids, has expressed interest. Even private companies have proposed missions, some funded by philanthropists, who see planetary defense as a cause worthy of personal investment. The 5th and final response to the Apophis challenge is the one that receives the least attention, but may ultimately prove the most important. It is the slow, grinding, unglamorous work of building an international planetary defense infrastructure. The legal frameworks, communication protocols, decision-making processes, and funding mechanisms that would be needed to respond to a confirmed impact threat. This work is being done by a small community of scientists, engineers, lawyers, and policy analysts scattered across agencies and universities around the world. They convene at biannual planetary defense conferences where they run tabletop exercises, simulations of asteroid impact scenarios designed to test the response chain from detection to deflection. These exercises have been sobering. In one such exercise, conducted in 2019, participants were presented with a fictional asteroid board discovered on a collision course with Earth, with 8 years of warning. The exercise revealed that even with 8 years, the time needed to mount a deflection mission was barely sufficient. Decision-making was paralyzed by uncertainty about the asteroid's properties. International coordination was hampered by differing national interests, and public communication was complicated by conflicting scientific assessments that were quickly distorted by social media. In another exercise, conducted in 2021, the fictional scenario gave only 6 months of warning. The result was unambiguous. With 6 months, deflection was not possible by any currently available technology. The only options were evacuation and civil defense, moving people out of the predicted impact zone and hoping the predictions were accurate enough to identify the zone correctly. With a positional uncertainty of hundreds of kilometers, that meant evacuating entire nations. These exercises are not pessimistic fantasies. They are honest assessments conducted by the people who would be responsible for responding to a real threat, and the conclusions are consistent. Our detection capabilities are improving, but our response capabilities lag far behind. The gap between finding an asteroid and doing something about it remains dangerously wide. The math is striking. Since Apophis was discovered in 2004, the global catalogue of known near-Earth asteroids has grown from roughly 3,000 to over 35,000. Detection is working. The surveys are finding objects. The orbits are being computed. But of those 35,000 objects, fewer than a handful have been studied in enough detail to plan a deflection mission, and only one, Dimorphos, has ever been the target of an actual deflection test. One object out of 35,000. That is the current state of planetary defense, and the clock continues to tick. There is a moment in the study of asteroid impacts when the numbers stop being numbers and start being something else entirely, something that settles into the chest and stays there. The moment is not dramatic. It does not arrive with a crash or a flash of light. It arrives quietly, the way the most important realizations always do, in the silence between one thought and the next. Here is the realization. The Earth is 4.54 billion years old. In that time, it has been struck by millions of asteroids. The evidence is everywhere. In the ancient craters now eroded to subtle rings, visible only from orbit. In the iridium layer that marks the Chicxulub impact in sedimentary rock around the world. In the pockmarked faces of the Moon and Mercury and Mars, which bear the scars of impacts that would have been equally devastating on Earth, but which our planet's atmosphere and geology have slowly erased. Every surface in the inner solar system tells the same story. Impacts are not rare, they are not unusual. They are the fundamental mechanism by which the solar system was built, and they have not stopped. What is rare, what is genuinely unprecedented in the 4.5 billion year history of this planet, is that something is alive on its surface that can see them coming. That is the deeper truth of Apophis, not the asteroid itself, not its orbit, not its composition or spin rate or Yarkovsky drift. The deeper truth is us. We are the first, and so far the only, beings in the known history of the solar system who can detect an approaching asteroid, calculate its trajectory, and contemplate a response. The dinosaurs could not do this. The trilobites could not do this. The single-celled organisms that dominated the first 3 billion years of Earth's history could not do this. We can, and we have been able to do it for less than 30 years. Let that sink in. In the entire history of life on this planet, a span of roughly 3.8 billion years, the window during which any living creature has possessed the awareness and the technology to detect an incoming asteroid is less than 30 years wide. That is a ratio so extreme that it defies intuitive comprehension. It is like a person who has been alive for 80 years becoming aware of traffic for the first time in the last tenth of a second of their life. Everything before that moment was spent walking blindly across highways, surviving not through awareness, but through sheer statistical luck. And the luck has not always held. The fossil record is punctuated by mass extinctions, moments when the thread of terrestrial life was nearly severed. The Chicxulub impact 66 million years ago killed 75% of all species. The Permian-Triassic extinction 252 million years ago killed roughly 96% of marine species and 70% of terrestrial vertebrate species. And while its primary cause was likely volcanic, there is evidence that impact events may have contributed. The late Devonian extinction, the Triassic-Jurassic extinction, the Ordovician-Silurian extinction, each one reshaped the trajectory of life on Earth, closing some evolutionary paths forever and opening others. We are the inheritors of that trajectory. Every cell in your body carries the legacy of organisms that survived those extinctions, not because they were clever or strong, but because they happened to be in the right place at the right time, possessing the right traits to endure the particular flavor of devastation that their era delivered. Luck. Blind, statistical, cosmic luck. And now, for the first time, we have something better than luck. We have knowledge, we have telescopes, we have radar, we have spacecraft, we have the mathematical frameworks to predict an asteroid's trajectory decades in advance. We have, as DART demonstrated, the rudimentary ability to move an asteroid off course. The tools are imperfect, the infrastructure is incomplete, but they exist, they are real, and their existence marks a turning point in the history of life on this planet that is as profound, in its way, as the emergence of photosynthesis or the colonization of land. This is not science fiction. This is the factual assessment of where we stand. A species that arose on the African savanna roughly 300,000 years ago that spent most of its existence hunting, gathering, and telling stories around fires, has built instruments capable of detecting a 370-meter rock at a distance of hundreds of millions of kilometers and calculating where it will be to within a few hundred meters a quarter century from now. That is extraordinary. It is worth pausing to feel the weight of it. But the weight comes with a shadow, because awareness without action is merely anxiety. And that is the uncomfortable position in which humanity currently finds itself. We can see the threat, we can measure it, we can name it, but our ability to respond, to actually stop an asteroid on a collision course, is still in its infancy. Consider the scenario that planetary defense scientists call the nightmare case. A previously unknown asteroid, roughly 300 meters in diameter, similar in size to Apophis, is discovered emerging from the sunward blind spot on a trajectory that will bring it to Earth in approximately 18 months. 18 months of warning. That sounds like a lot. It is not. Designing, building, and launching a kinetic impactor takes, under the most optimistic assumptions, 2 to 3 years, using existing spacecraft bus designs and launch vehicles. A gravity tractor, which requires hovering near the asteroid for years to slowly tug its orbit, is useless on an 18-month timeline. A nuclear standoff detonation, while physically effective, faces political and legal obstacles that could consume months of the available warning time in negotiations alone. And if the asteroid is a rubble pile, a loose collection of boulders held together by gravity and friction, as many near-Earth asteroids are, a kinetic impactor might simply punch through it without significantly altering its trajectory, or worse, break it into multiple pieces that create a shotgun effect on a wider area. 18 months, that is the nightmare. And it is not far-fetched. The Chelyabinsk asteroid came with 0 months of warning, 0 days, 0 hours. It appeared in the sky above Russia and detonated before anyone on the ground had time to react. If that object had been 18 times larger, Apophis-sized, the story would not be about broken windows in Chelyabinsk. It would be about a city that no longer exists. The deeper truth of Apophis is that it is a messenger, not a messenger of doom. The orbit calculations have relieved us of that immediate fear, but a messenger of vulnerability, a reminder that the solar system is not a museum, not a static display of pretty planets and distant stars. It is a dynamic, violent environment where objects of terrifying energy traverse the same space we occupy, on timescales that are both longer than human memory and shorter than human planning. There is a concept in risk assessment called a black swan event, a high-impact occurrence that is rare, unpredictable, and, after the fact, rationalized as having been inevitable. Asteroid impacts are the cosmic equivalent. Every major impact in Earth's history would have seemed impossible the day before it happened. And yet, in retrospect, each one was simply the inevitable result of orbital mechanics playing out over sufficient time. Apophis forces us to confront a particular flavor of this vulnerability, the vulnerability of timing. If Apophis had been discovered not in 2004 but in, say, 1884, the discovery would have been a scientific curiosity and nothing more. No one in 1884 had the technology to track an asteroid's orbit with precision, let alone deflect one. The discovery would have been published, debated, and forgotten. And if the orbit had, in that alternative timeline, been a collision course, humanity would have had no idea until the flash of light and the wall of fire. If Apophis had been discovered in 2024, just 5 years before its 2029 close approach, the warning time would still have been sufficient to determine that it would miss. But if the orbit had been a collision course, 5 years would have been barely enough to mount a deflection. The mission planning, the spacecraft construction, the launch window calculations, the interplanetary crews, the terminal guidance, all compressed into a timeline that leaves almost no margin for delay, failure, or surprise. We were lucky that Apophis was discovered 25 years before its closest approach, lucky that the orbit turned out to be a miss, lucky that the additional observations were available to resolve the uncertainty, lucky that the Yarkovsky effect could be measured in time. Lucky. And luck is not a strategy. Let that sink in. The scientists who have dedicated their careers to planetary defense understand this with a clarity that borders on obsession. They are not alarmists, they are not doomsayers. They are mathematicians, physicists, and engineers who have stared at the numbers long enough to understand what they mean and what they do not mean. The numbers say that an Apophis-sized impact happens, on average, once every 80,000 years. The numbers also say that on average is a meaningless comfort when the events are random. The next one could be tomorrow. The next one could be in 50,000 years. The probability distribution is flat and pitiless, and it does not care about averages. What the numbers do say, with chilling precision, is that the solar system contains enough asteroids on enough intersecting orbits with enough velocity to render the surface of the Earth uninhabitable for any species that lacks the ability to see them coming and move them aside. We have, within the last generation, acquired the first of those abilities, imperfectly, incompletely, but genuinely. The second ability, the ability to act, exists only as a proof of concept, a single test mission against a target that posed no threat. There is a phrase that echoes through the planetary defense community. It is attributed to various scientists and has been repeated in so many forms that its original author is unclear, but its meaning is precise. The dinosaurs went extinct because they did not have a space program. We have one. The question is whether we will use it. That question is not rhetorical. It is not a motivational poster. It is a genuine, urgent, operational question that will be answered, one way or another, by the choices that governments, space agencies, and taxpayers make in the coming decades. The Apophis flyby of 2029 will provide a moment of global attention, a window during which the sky itself will deliver a visual reminder of the threat. Whether that moment is used to accelerate planetary defense or merely consumed as entertainment is, as of tonight, undecided. And there is one more aspect of the deeper truth that deserves to be spoken plainly, because it touches on something that most discussions of planetary defense politely avoid. It is the question of equity. If an asteroid impact is predicted for a specific region of the Earth, who decides how to respond? Who decides whether to attempt deflection, with its attendant risks of fragmentation or miscalculation, or to evacuate? Who bears the cost? Who bears the risk? And whose lives are weighed in the calculation? The Torino scale, the system used to communicate asteroid impact risks to the public, rates events from 0 to 10 based on the combination of impact probability and kinetic energy. It is a useful tool, but it is a scientific tool, not a moral one. It tells you how dangerous an asteroid is. It does not tell you what to do about it, and the decisions that would need to be made in a real impact scenario, where to aim a deflection spacecraft, whose territory to overfly, what nuclear treaties to invoke or set aside, who to evacuate and who to leave in place, are not scientific decisions. They are political decisions, ethical decisions, and ultimately human decisions that no equation can resolve. Apophis, by missing, has given us the luxury of considering these questions in the abstract. The next asteroid may not be so generous. The deeper truth, then, is not one truth but several, layered like the geological strata that record Earth's violent history. The solar system is dangerous. We are fragile. We are aware. We are not yet ready. And the window between awareness and readiness is the most consequential window in the history of our species, because it is the window in which we must decide whether to become the first form of terrestrial life that can survive its own cosmic environment, or the most recent to go extinct, despite having the chance to prevent it. Every atom in your body was forged inside a dying star. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was synthesized in the nuclear furnace of a star that exploded billions of years ago, scattering its debris across the galaxy, where it coalesced into new stars, new planets, and eventually new life. You are, in the most literal sense, the universe contemplating itself. And the asteroid named Apophis, that tumbling, peanut-shaped rock of iron and silicate, is made of the same stuff. The same atoms, forged in the same stellar fires, drifting through the same void. The difference is that you are aware of the encounter. Apophis is not. And that awareness, fragile, recent, hard-won, is the only thing standing between civilization and the indifferent mathematics of orbital mechanics. The question is whether awareness will be enough. There is a final dimension of this deeper truth that merits contemplation, and it concerns not the threat itself, but the strange, paradoxical beauty of the encounter that awaits us in 2029, because Apophis is not only a warning, it is also, in the most unexpected way, a gift. On the evening of April 13, 2029, across a swath of the Earth, stretching from the Eastern Hemisphere through Europe and Africa, people will be able to step outside and watch a point of light, faint but visible, drift slowly across the sky. It will first be visible in the constellation of Cancer, moving through it, and into the constellation of Leo over the course of a few hours. At its brightest, it will reach roughly visual magnitude 3.1, comparable to the faintest stars of the Big Dipper, easily visible from a dark sky location, and just barely visible from a suburban backyard. Think about what that means. For the first time in human history, a named, catalogued, potentially hazardous asteroid will be visible to the unaided human eye during a predicted close encounter. Every previous close approach of a significant asteroid has been invisible, detectable only through telescopes, recorded only in data files and journal papers. This one will be different. This one you can see. The timing is striking in itself. Apophis will make its closest approach at approximately 21:46 Coordinated Universal Time, roughly 9:46 in the evening across much of Western Europe, late afternoon in the eastern United States, and nighttime across the Middle East and parts of Africa. For observers in those regions, the asteroid will be well placed in the evening sky, rising in the east and tracking westward as it reaches peak brightness and then begins to recede. The speed of its passage across the sky will be noticeable even to casual observers. Because of its proximity, Apophis will exhibit detectable apparent motion over the course of minutes, not hours, through binoculars or a small telescope, it will appear to move against the background stars in real time, like a slow-moving satellite, except that satellites are tiny, metallic, and close. This is a mountain of rock, farther away than any satellite, and the fact that it is moving visibly across the sky is a testament to how close it truly is. Astronomers around the world are planning observation campaigns that border on the unprecedented. Every major optical telescope capable of tracking a fast-moving object will be pointed at Apophis during the flyby window. Radar facilities at Goldstone and potentially at newly upgraded installations will be bouncing signals off its surface, measuring distance, velocity, shape, and spin with precision never before achieved for an asteroid of this size. Infrared telescopes will measure its thermal properties. Spectroscopes will analyze the composition of its surface. And citizen scientists, amateur astronomers with modest equipment, will contribute observations from locations around the globe, adding to the dataset with a coverage that no single observatory can match. The scientific returns are expected to be extraordinary. Before the flyby, Apophis is a distant object known primarily through brief windows of observability. After the flyby, it will be the most thoroughly characterized potentially hazardous asteroid in existence. Its shape, size, mass, density, surface texture, mineral composition, spin state, and thermal properties will all be measured to a precision that currently exists for only a handful of asteroids, most of which have been visited by spacecraft. And there is one measurement that excites planetary scientists above all others. During the close encounter, Earth's tidal forces will stress the asteroid's interior. If Apophis has internal fractures, loose rubble, or structural weaknesses, the tidal forces may cause visible changes. Landslides, dust emission, surface disruption, or even a subtle change in shape. Detecting these changes would provide the first direct evidence of how a potentially hazardous asteroid responds to gravitational stress at close range. This information is critical for deflection planning. An asteroid that crumbles under tidal stress would respond very differently to a kinetic impactor than one that remains structurally intact. And we have never had the chance to observe this process in real time. OSIRIS-APEX will arrive in the Apophis system roughly a month after the Earth flyby and will settle into orbit around the asteroid for at least 18 months. During that time, it will produce a detailed map of the surface at resolutions of meters to centimeters, revealing every boulder, every crater, every fracture, and every change wrought by the Earth encounter. It will also fire its thrusters close to the surface to disturb loose regolith, observing how the material behaves in the asteroid's extremely low-gravity environment. The surface gravity of Apophis is roughly 100,000 times weaker than Earth's. A pebble tossed upward at walking speed would take hours to come back down, and might not come back down at all. This low-gravity environment is itself a subject of intense scientific interest, because it governs how asteroids of this size hold themselves together. Below a certain size, roughly a few hundred meters, asteroids are thought to be dominated by cohesive strength, meaning the material itself holds the body together the way a rock holds itself together on Earth. Above a certain size, perhaps a few kilometers, asteroids are gravitationally bound, held together by their own gravity, despite having almost no structural strength. In between these regimes, Apophis's regime, the situation is unclear. The asteroid may be a solid monolith, a fractured but coherent body, or a gravitational aggregate of loosely bound fragments. Determining which of these descriptions is correct has enormous implications for planetary defense. A solid monolith can be deflected by a single kinetic impact. A fractured body might require a more carefully calibrated approach. And a gravitational aggregate, a rubble pile, might simply absorb the impact energy, deforming but barely changing course, or might fragment into a swarm of smaller pieces, each one large enough to cause significant damage. The DART mission struck Dimorphos, which is believed to be a rubble pile. The result was a larger than expected orbital change, primarily because of the ejector enhancement. But Dimorphos is only 160 meters across, less than half the size of Apophis. Whether the same physics applies at larger scales, where gravity plays a larger role, is unknown. That word appears over and over in the scientific literature about Apophis, and it is a word that should carry more weight than it typically does. In everyday conversation, unknown is a gap, an absence, a detail to be filled in later. In planetary defense, unknown is a variable that could mean the difference between a successful deflection and a catastrophic failure. It is the margin of ignorance within which a civilization could be lost. The 2029 flyby will shrink that margin, not eliminate it. A single encounter cannot answer all the questions, but shrink it. And in planetary defense, shrinking the margin of ignorance is the most valuable work that can be done, because every unknown we resolve today is one fewer crisis we face tomorrow. There is a passage from the physicist Richard Feynman that resonates here, though he was speaking of science in general, not of asteroid defense specifically. He said, "The first principle is that you must not fool yourself, and you are the easiest person to fool." Apophis has forced the scientific community to confront this principle directly. For years, the comfortable assumption was that a large, dangerous asteroid would be found decades before any potential impact, providing ample time for deflection. Apophis showed that the discovery-to-threat timeline can be alarmingly short. The Chelyabinsk event showed that it can be zero. The comfortable assumption was wrong. The question is whether we will remember that lesson, or whether the passage of Apophis across the April sky will become just another viral moment in an endless feed, forgotten by the time the rock clears the moon's orbit. That is the choice. That is the deeper truth distilled to its simplest form. Apophis is coming. It will pass. It will not hit us. But what we do with the knowledge it delivers, what missions we fund, what telescopes we build, what systems we deploy, what plans we make for the day when the math breaks differently, will determine whether we are the species that learned from the warning or the species that ignored it. The universe offers very few second chances. Apophis is one of them. And there is one more gift that Apophis offers, one that transcends the scientific and enters the realm of the deeply personal. It is the gift of perspective. Modern life is lived at the scale of the immediate. The concerns that fill our days, deadlines, bills, relationships, health, politics, are real and important, but they exist on a timescale measured in days, months, and years. The asteroid named Apophis exists on a timescale measured in millions of orbits, billions of years of solar system history, and a future that stretches to the heat death of the universe. When you look up at that faint point of light in the April sky, you are looking at something that was orbiting the sun before there were humans, before there were primates, before there were mammals. It was circling the sun when the dinosaurs walked the earth. It was there when the first fish crawled onto land. It was there when the oceans formed, and the magma cooled, and the proto-Earth accreted from a disk of dust around a young star. And it will still be there, on some orbit, in some form, long after our species has either spread to the stars or vanished from the fossil record. The asteroid does not know we exist. It does not know that a small group of primates on the third planet from the Sun gave it a name and calculated its trajectory and argued about how to defend themselves against it. It simply follows the laws of physics with a fidelity that no human institution can match. There is something clarifying about that, something that strips away the noise and urgency and the triviality of the daily churn and leaves only the essential question: what kind of species are we? Are we the kind that sees a warning and heeds it? Are we the kind that builds the tools and institutions needed to protect not just ourselves, but our descendants? Generations who will never know our names, but who will inherit either our foresight or our negligence. The answer is not yet written. The answer is being written right now, in the budgets and mission plans and political decisions of the 2020s. It will continue to be written in the decades that follow. And on April 13th, 2029, the universe will provide a moment of clarity, a brief, bright reminder that the question is real, that the stakes are absolute, and that the window for action is not infinite. We have walked through the discovery, the scare, the science, the missions, and the deeper meaning. We have followed the story from a pair of faint dots on a CCD image in Arizona to a global reckoning with cosmic vulnerability. We have watched scientists argue, governments hesitate, telescopes collapse, and spacecraft slam into distant rocks at 6 kilometers per second. We have stared at numbers that defy intuition and probabilities that defy comfort. And through it all, the rock named Apophis has continued its steady, silent orbit, indifferent to our fear, our ambition, our progress, and our failure. It crosses the orbit of Venus on its inward swing. It crosses the orbit of Earth on its outward reach. It tumbles slowly in the vacuum, warmed on one side by the sun, cooled on the other by the void. It has been doing this for billions of years. It will continue doing this for billions more, unless one day it meets something in its path, a planet, a moon, another asteroid, or a spacecraft sent by a species that finally decided to take the threat seriously. That decision is the hinge on which the future turns. And as we move now into our final reflections, it is worth holding that image, the hinge, the turning point, the moment of choice, clearly in mind. Because the story of Apophis is not over. It is barely beginning. The 2029 flyby is not the climax. It is the opening act of a story that will unfold across centuries, as humanity either builds the planetary defense infrastructure it needs or fails to do so. And the consequences of that story, success or failure, survival or extinction, will be measured not in news cycles or election terms, but in geological time. The philosopher Hannah Arendt once observed that the most radical transformation in human thought was the moment we realized we could observe the Earth from outside it, the moment of cosmic perspective. Apophis offers a variation on that theme. It is not a view of the Earth from outside. It is a view of the Earth's future from within. When we track this asteroid, when we calculate its orbit, when we measure the Yarkovsky drift, pushing it 170 meters per year along its path, we are not simply doing astronomy. We are performing an act of self-awareness at a species level. We are acknowledging, with mathematical precision, that we live on a small planet in a vast and indifferent cosmos, and that the forces which shaped that cosmos, gravity, velocity, the cold geometry of elliptical orbits, do not distinguish between an uninhabited rock and a world full of cathedrals and children and music. That acknowledgement is, in a strange way, the most hopeful thing about the Apophis story, because it means we are paying attention. It means that the long experiment of human intelligence has produced, among its many outputs, the capacity for planetary self-defense. Not the perfected capability, not yet, but the capacity, the seed, the beginning of a process that, if nurtured, could make us the first species in 4.5 billion years to survive not by luck but by design. There is a word for this in the vocabulary of planetary science. The word is resilience. It is the quality that separates a system that can absorb a shock and continue functioning from one that collapses under stress. The Earth's biosphere has resilience. It has survived 5 major mass extinctions and recovered each time, though the recovery took millions of years, and the species that emerged were not the ones that went in. Our civilization, by contrast, has never been tested against an impact event. We do not know what our resilience is. We do not know whether our interconnected, globalized, technologically dependent society could absorb the shock of 1,000 megaton impact and survive intact, or whether the cascading failures, disrupted supply chains, collapsed communications, agricultural devastation, political fragmentation, would unravel the fabric of modern life in ways that we cannot predict and might not recover from for centuries. What we do know is that the tools to prevent such a scenario exist, in principle, if not yet in practice. We know that detection is possible, that deflection is possible, and that the physics of planetary defense is well understood. What remains is the engineering, the funding, the political will, and the institutional architecture to translate possibility into readiness. That is the work of the coming decades. It is work that will be difficult, expensive, and often invisible to the public. Not the stuff of dramatic headlines, but the slow, steady construction of a capability that may never be needed in our lifetimes, or may be needed tomorrow. The Apophis flyby of 2029 will be a test of something more than telescopes and radar dishes. It will be a test of attention, a test of whether a species that routinely ignores slow-building threats, climate change, antibiotic resistance, soil depletion, can summon the focus to address a threat that is, on any given day, invisible and silent. The asteroid will not knock on our door. It will not send a letter. It will simply be there, on its orbit, following the laws of physics with perfect indifference, and we will either be ready for it, not this time, but next time, or we will not. The deeper truth is not that the sky is falling. The deeper truth is that the sky has always been falling, and we are the first generation of any species on this planet to know it. What we do with that knowledge will define us more completely than any other choice we make. More than our art, more than our technology, more than our wars or our treaties. Whether we choose to protect the small, fragile, irreplaceable world that is our only home, or whether we look up at the asteroid drifting across the evening sky, shrug, and go back inside. That is the question Apophis asks, not with language, not with intent, but with the brute, silent eloquence of mass and velocity, passing 31,860 kilometers above the surface of the only planet in the known universe where anyone is listening. We have traveled a long road tonight, from the first detection of a faint point of light on a CCD image in Arizona to the global reckoning with cosmic vulnerability that followed. The story of Apophis is one of the most remarkable narratives in the history of science, not because of the asteroid itself, but because of what it revealed about us. It revealed that we are capable of extraordinary precision. The fact that a team of astronomers could detect a 370-meter rock at a distance of tens of millions of kilometers, track its motion across the sky, compute its orbit through the gravitational fields of 8 planets and the Sun, measure the subtle thermal thrust of the Yarkovsky effect to within a few dozen meters per year, and predict its position a quarter century in the future to within a few hundred meters. That is an achievement of human intelligence that stands alongside any in our history. The tools are different from those of the Renaissance or the Enlightenment, but the impulse is the same: to see clearly, to measure precisely, and to understand deeply. It revealed that we are capable of bold action. The DART mission, for all its limitations, was a genuine first, a deliberate, successful alteration of a celestial body's orbit. It was not a theoretical exercise. It was not a computer simulation. It was a half-ton spacecraft slamming into a rock at 6 kilometers per second and measurably changing the trajectory of that rock. The physics worked. The engineering worked. The concept was proven. Humanity can, in principle, defend itself against an asteroid impact. That statement was not true 20 years ago. It is true now. But the story also revealed something less flattering. It revealed that we are slow. Slow to fund, slow to build, slow to act. The gap between the Apophis scare of 2004 and the DART impact of 2022 was 18 years. The gap between the congressional mandate to find 90% of hazardous asteroids larger than 140 meters and the projected achievement of that goal is likely to exceed 30 years. The NEO-Surveyor telescope, a mission whose need was obvious by the mid-2000s, has been in various stages of proposal, review, delay, and development for nearly 2 decades. This slowness is not unique to planetary defense. It is a feature of democratic governance, of competing priorities, of the human tendency to defer action on threats that feel distant and improbable. But in the context of asteroid defense, the cost of slowness is potentially existential. An asteroid does not wait for an appropriations bill. It does not pause while a mission undergoes peer review. It follows its orbit with a regularity that borders on the mechanical, and if that orbit intersects the Earth's, the only variable that matters is whether we have placed something in its path to alter the outcome. The implications of the Apophis story extend far beyond the field of planetary defense. They touch on the broader question of how human civilization relates to existential risk that is low in probability but catastrophic in consequence. We are, by nature, bad at reasoning about such risks. Our intuitions are calibrated for the immediate, the personal, the tangible. A risk that is 1 in 10,000 per century feels, to the human brain, like a risk of 0. It does not trigger the alarm systems that evolved to protect us from predators and rivals. It does not generate the emotional urgency that drives political action. And yet, the mathematics of existential risk is unforgiving. A 1 in 10,000 chance of an event that kills millions is not a negligible risk. It is a risk that, over sufficient time, becomes a certainty. The question is not whether such an event will occur, but when, and whether, when it does, we will have invested enough foresight to survive it. Apophis has given us a framework for thinking about this. It has shown us that the threat is real, that the tools for addressing it exist, and that the primary obstacle is not scientific or engineering, it is political and psychological. The challenge is not building a better telescope or a faster spacecraft. The challenge is convincing a species that evolved to fear lions and lightning to also fear a rock that is invisible to the naked eye and may not arrive for another 80,000 years. But perhaps that is too pessimistic a framing. Perhaps the better framing is this. The fact that we know about Apophis at all is extraordinary. The fact that we can calculate its orbit, measure its thermal properties, predict its close approach to within 100 meters, and send a spacecraft to study it up close. These are not signs of a species that has failed. They are signs of a species that is learning. Learning slowly, yes. Learning imperfectly, yes. But learning. The 2029 flyby will be a milestone in that learning. Not the final milestone, not even close, but a significant one. It will provide data that no other event can provide. It will capture public attention in a way that no press release or scientific paper can match. And it will force a conversation among scientists, among policymakers, among ordinary people looking up at the sky on an April evening about what we are willing to do to protect the planet that is our only home. That conversation has been happening in fragments and fits since Apophis was discovered. It has produced real results. DART, OSIRIS-APEX, NEO-Surveyor, the Planetary Defense Coordination Office, the international frameworks for threat assessment and response. But it has not yet produced the sustained, funded, global commitment that the threat demands. The question of the coming decade is whether the 2029 flyby will catalyze that commitment, or whether it will be consumed as spectacle and forgotten. History offers cautionary examples. The Tunguska event of 1908, an airburst over Siberia that flattened 2,000 square kilometers of forest, generated scientific interest but no sustained investment in planetary defense. The Chelyabinsk event of 2013 generated a burst of media coverage and a modest increase in survey funding, but no fundamental change in policy. Whether the 2029 Apophis flyby follows the same pattern or breaks it will depend on choices that have not yet been made, and those choices will shape the future of our species in ways that are difficult to overstate. Because the story of Apophis is not, in the end, a story about one asteroid. It is a story about a turning point, the moment when a species that had always been at the mercy of the cosmos first glimpsed the possibility of taking control. Not control of the cosmos, that is beyond any species, but control of its own fate within the cosmos, the ability to see a threat, measure it, and choose to act. That ability is new, it is precious, and it is not guaranteed to last. Civilizations can decline, technologies can be lost, priorities can shift. The fact that we can detect asteroids today does not mean we will be able to detect them in 500 years. The fact that we can deflect one today, barely, tentatively, under ideal conditions, does not mean that capability will be maintained and improved over the centuries it will take to face the next Apophis. The window is open. The question is whether we will walk through it. On April 13th, 2029, a point of light will appear in the evening sky. It will drift slowly across the constellations, visible to anyone with clear skies and a willingness to look up. It will be bright enough to see without a telescope, a faint star among stars, unremarkable to anyone who does not know what it is. But for those who do know, for the astronomers and engineers and policymakers and ordinary citizens who have followed this story, that point of light will carry a weight that no star can match. Because it is not a star, it is a rock, a mountain of iron and silicate, 370 meters across, hurtling through space at 31 kilometers per second, and it will be passing closer to Earth than the satellites that carry your phone calls. 31,860 kilometers, that is the distance. If you could drive there at highway speed, 100 kilometers per hour, without stopping, it would take about 13 days. 13 days of driving to reach an object that, if its orbit had been fractionally different, would have struck with the force of 20,000 Hiroshima bombs. But it will not strike. The orbit is known, the math has been done, the radar has pinged, the telescopes have tracked, the Yarkovsky drift has been measured. Apophis will miss. It will bend around us, reshaped by our gravity, and continue on its new orbit, an orbit that has been certified safe for the next 100 years. That is the answer to the title question, stated as plainly as science allows. The asteroid passing closer than satellites in 2029 will not hit the Earth. Not this time. Not on this pass. Not in the foreseeable future. But the answer to the larger question, the question that Apophis asks by its very existence, is far more complex. Because the next Apophis is already out there. It is orbiting the Sun right now, on a path that has not yet been calculated, through a solar system that does not care about our timelines or our budgets. It might be found tomorrow by a survey telescope in Chile. It might be found in 50 years by a space-based infrared observatory. Or it might not be found at all until it appears as a streak of light in the atmosphere. Too fast and too close for anyone to do anything but watch. The solar system is 4.5 billion years old. It has been throwing rocks at Earth since the beginning. The craters are there, on every continent, on every ocean floor, on the Moon and Mercury and Mars. The fossil record is there. The iridium layer, the mass extinctions, the evolutionary bottlenecks that shaped the tree of life. The threat is there, not as a distant abstraction, not as a Hollywood plot device, but as a mathematical certainty spread across a timescale that mocks human planning. And against that threat, for the first time in the history of life on this planet, there is a response. Imperfect, incomplete, underfunded and understaffed, and spread across a patchwork of agencies and nations that cannot always agree on how to coordinate. But real, a species that can see the rock coming, that can calculate where it will be in 25 years, that has at least once successfully pushed a rock off course, that is building, slowly, grudgingly, but building, the infrastructure to do it again, better, faster, and at the scale that the threat demands. That is the story of Apophis, not a story of doom, not a story of salvation, a story of awareness, the moment when humanity opened its eyes, looked up and saw for the first time the true nature of the sky it lives under, not a ceiling, not a dome, not a painted backdrop of harmless stars, but a vast, dynamic, occasionally violent environment where objects of staggering energy cross our path on timescales that are, from the cosmic perspective, routine. If the sun were a basketball sitting on a field in Cairo, Apophis would be a grain of sand roughly 60 meters away, drifting past at a speed too slow to see but too fast to stop. And Earth, the only planet in the known universe where anyone is aware of this encounter, would be a small marble sitting in the path of a grain of sand that carries enough energy to reshape continents. The grain of sand will miss the marble this time. The geometry has been checked, the math holds, but the field is full of grains of sand, and the marble is not moving, and the only thing protecting it is a handful of telescopes, a tested-once deflection method, and the sustained attention of a species that is very, very good at looking away. On April 13th, 2029, do not look away. Step outside. Find the constellation Cancer in the eastern sky. Look for a faint point of light that does not belong, a point that is moving, slowly but perceptibly against the fixed background of stars. That is Apophis. That is a reminder, not a threat, not this time, but a reminder that the universe is not gentle, that the margins are thin, and that the only species in 4.5 billion years of terrestrial life that can see the rock coming has a responsibility to itself, to its descendants, and to every form of life that shares this fragile, irreplaceable world, to be ready when the next one arrives. The rock will pass, the stars will remain, and the silence that follows will be the most important silence you have ever heard, because it will be the sound of a species that survived not by luck, not by accident, but by looking up and choosing to pay attention. That is all we can do, that is everything we must do, and it is enough if we choose it. And in the end, that faint point of light, drifting quietly across the April sky, will carry a message that no words can improve. We are here, we are aware, and for the first time in the long, unbroken history of this ancient, battered, beautiful planet, we have a chance.